Swayam Prabha. Digital India. Educated India.
Welcome to the Organic Chemistry Paper 2. In the Module 7, we will be studying about acids and its derivatives. In the Lecture 1, we will be studying about preparation and reactions of carboxylic acids. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. Let us look at the topics that will be covered in this particular session. We will be studying about preparations of acids, mainly many of the oxidation methods, Grignard reaction, hydrolysis method, and the special methods of phenolic acids. So these are all the reactions we will be studying about for the preparation of carboxylic acids. And we will also be studying about various reactions of acids, that is mainly esterification, both acid and base catalyzed reactions. We will be studying about conversion of acids to acid chlorides, anhydrides, and amides. We will also be studying about various reduction reactions of carboxylic acid, halogenation, and sticker reaction. So these are all the various reactions that we will be studying about carboxylic acids. Welcome to the next session. In this particular session, we will be studying about preparations of carboxylic acids. Let us look at the different methods of preparation of carboxylic acids. The first one is oxidation of primary alcohols. Then we will be studying about oxidation of alkyl benzenes. We will be studying about carbonation of Grignard reagents. Then we will be studying about hydrolysis of nitriles, malanoic acid synthesis, and special methods for the synthesis of phenolic acids. So first let us start about the preparation of acids from alcohols. So this is a primary alcohol shown here. When a primary alcohol is subjected to oxidation using potassium dichromate under acidic conditions, provides carboxylic acid. This is a very straightforward method. Then the next method is the primary alcohol can also be converted to carboxylic acid by a different route. We will now look at what is this route. In this route, the first step is the treatment of primary alcohols with PX3. So we have already seen in the alkyl halide preparation the treatment of primary alcohol with PX3, that is phosphorus trihalides, produces the corresponding halo derivative. It can be chlorobromo. So once we have the halogen alkyl halide, we can treat that with magnesium to make the corresponding Grignard reagent. So this reaction also we had seen in the case of alkyl halides. So treatment of magnesium with alkyl halide in the presence of dry ether produces the corresponding alkyl magnesium halide. So this alkyl magnesium halide can be treated with carbon dioxide gas. Generally in this particular reaction, carbon dioxide gas is not used, actually dry ice. The solidified carbon dioxide at minus 78 degrees centigrade gives a solid carbon dioxide. So after the preparation of this Grignard reagent, that reaction we add solid CO2, so that is the dry ice, and this gives the intermediate which on hydrolysis provides the corresponding carboxylic acid. Here if we start from the carboxylic acid RCH2OH molecular formula, we are getting RCH2COOH. So one carbon extra is added to this starting primary alcohol. So there is another method. This alkyl halide can be treated with cyanide nucleophile. So basically potassium cyanide can be used to convert the corresponding halo derivative into the cyano derivative. So that is also possible. So when we treat this cyano derivative with acidic or basic conditions, this undergoes hydrolysis to provide the corresponding carboxylic acid. So in this particular path also there is a addition of one carbon from the starting primary alcohol. So these two methods, like conversion of the alcohol to alkyl halide and treatment with CO2 after the formation of the Grignard reagent giving the carboxylic acid, or alkyl halide when treated with a cyanide nucleophile giving the carboxylic acid after hydrolysis. In both the process there is a increase in one carbon, that is one carbon elongation or homologation of the primary alcohol is possible. So this way we can make a new carboxylic acid from the primary alcohol. So in the previous method what we have seen is the primary alcohol can be directly oxidized to carboxylic acid with the same number of carbon atoms using potassium dichromate under acidic conditions. When we follow this path we have one carbon extra. So these are all the two different methods by which a primary alcohol can be converted to carboxylic acids. Then we will also look at a few other oxidation methods. In this case, the primary alcohol can be oxidized using potassium dichromate, which can give a aldehyde. Of course, this aldehyde is never isolated. This undergoes direct oxidation to produce the corresponding carboxylic acid. And the primary alcohol can also be directly oxidized to carboxylic acid using KMnO4 either under acidic or basic conditions. So this is also another method. So these two are a very good or strong oxidizing agents. And alcohol can be oxidized to carboxylic acid using silver oxide. This is a milder conditions because in this particular case the primary alcohols are not at all oxidized. So if we have to selectively oxidize a aldehyde group to a carboxylic acid group, as shown here, we can use silver oxide method. So this is a milder oxidizing conditions compared to the potassium dichromate or potassium permanganate oxidizing conditions. And when we have a secondary alcohol, so far we have seen this is a primary alcohol, and here we have a secondary alcohol. When we take a secondary alcohol and when we subject it to KMnO4 oxidation under acidic conditions followed by heating, this produces carboxylic acid. In this particular case, the reaction actually proceeds through a ketone intermediate. The secondary alcohol is converted to a ketone first, and which on treatment with the KMnO4 under heating conditions, this requires little harsh conditions to produce the carboxylic acids. So in this particular case, there are two ways the molecule can cleave, and the carboxylic acid, this bond when it cleaves we get a RCOOH, and the other unit also undergoes oxidation to give the carboxylic acid. So this way we can get two different carboxylic acids. And the next one is hydrolysis of cyanides. So here a cyanide is treated with either acid or base conditions to produce an amide, which is an intermediate in this reaction. Generally this amide is not isolated, which on further hydrolysis provides the carboxylic acid. Let us look at the mechanism of this hydrolysis of cyanides. First we will look at the acid catalyzed reaction. So in the acid catalyzed reaction, we already know there is a H plus ions present in the system. The nitrogen is nucleophilic or basic in nature. This has a lone pair of electrons. So whenever we have a electron rich species and a electron deficient species, the electrons are moving from the electron rich species to the electron deficient species. So the nitrogen gives its lone pair to the hydrogen and they form a bond. So this is an equilibrium reaction. In this particular case, now the nitrogen becomes positive charge. We already know nitrogen is comparatively more electronegative than carbon. So the plus charge cannot remain on the nitrogen for longer time. So what it does is, so this intermediate is quite unstable because there is a positive charge on a electronegative nitrogen. So this cannot exist for longer time. So what happens is this nitrogen now pulls the electron towards itself. So this C triple bond and one of the pi electrons are pulled towards the nitrogen, and now this carbon becomes electron deficient. To compensate that, what happens is a lone pair from the oxygen is given to the carbon. So we get this particular bond is, so we end up with this particular intermediate. And we already know this intermediate, the oxygen is having a positive charge. So oxygen cannot have a positive charge, so this proton, this hydrogen is lost as a proton and this bonded electrons are given to this particular oxygen. So the loss of H plus ion produces this particular intermediate. This intermediate is quite unstable, so this undergoes tautomerization, because if you look at these two structures, there is a hydrogen on the oxygen, there is a nitrogen having one hydrogen, but in the final product we have oxygen is not having a hydrogen but nitrogen is having two hydrogen. So what actually happens is, so one of this hydrogen actually gets transferred to this nitrogen. So this is a tautomerizing reaction that happens. So simply when it happens, basically the nitrogen's bond shifts towards this oxygen. So this proton is shifted to the nitrogen and this bonded electrons are shifted to the bond between carbon and oxygen. So what we end up is basically a amide unit. So this is how the cyanide is first hydrolyzed to the corresponding amide. So once the amide is formed, we are still having a acidic conditions. So there are a couple of ways can happen. This oxygen is having lone pair of electron. So this is electron deficient. So in this particular case, the nitrogen is having the lone pair that gave the electrons to this hydrogen to form the bond. Here this oxygen is more having two lone pair of electrons, whereas this nitrogen generally has only one lone pair. So this is much more prone to form a bond with the proton. So this gives the electron to form the bond with this proton. That leads to the formation of this particular intermediate. And as we already know, this oxygen is electron deficient right now, but this is an electron negative atom. So this wants to pull this bonded electron towards itself. Now the carbon will become electron deficient. To compensate that, what has to happen? This oxygen has to give its lone pair of electron to this particular carbon. So once this happens, then obviously the oxygen completely pulls the electron towards itself. So we have this particular intermediate formed, and if you compare this particular case and this particular case, in both the cases we have a carbon and an oxygen with a plus charge. Here also carbon and an oxygen with a plus charge. So we already know the same type of flow of electrons will happen because this oxygen cannot have a plus charge. So one of the hydrogen is lost as a proton. So like similar, here also we have a loss of proton, here also we have a loss of proton. That leads to this particular intermediate, a carbon with one OH unit, another OH unit and a NH2 unit. So this compound has 3 electron withdrawing groups, or the electronegative atoms are present on this particular carbon. So this is quite unstable. So what happens is one of the group has to leave. So let us see which group leaves now. So the lone pair of electrons from the oxygen is shifted between carbon and oxygen bond, and this NH2 group takes away this bonded electron and that leaves like a NH2 minus ion, and we have this particular species that is formed. Since the lone pair of electrons had shifted from the oxygen, then this becomes a positive charge. So we already know this cannot remain for longer. So the NH2 negative charged anion pulls this proton from this oxygen, so that this bonded electrons are shifted to the oxygen, so that we end up with the corresponding carboxylic acid and ammonia gas is also produced. So this way the cyanide hydrolysis produces carboxylic acid and ammonia. So this is the acid catalyzed hydrolysis of cyanide. We have just completed how the acid catalyzed hydrolysis happens for the nitrile. Now we will look at the base catalyzed hydrolysis. So in this particular case, we have a nitrogen which is more electronegative than the carbon. So this obviously will pull the bonded electrons towards itself. So that is what happens in the first step. So one of the pi bonded electrons are pulled towards the nitrogen, and now the carbon becomes electron deficient. So to compensate that, the base which is having electrons donates its electron to the carbon. So we end up with this particular intermediate. So this is the initial step in this particular reaction. So this intermediate is unstable. So what happens is nitrogen is having negative charge. So we have a H and OH bond is there. So the nitrogen forms a bond with the proton from the solvent molecule, water molecule. Now this HO bond is broken and it is polarized towards oxygen, or the oxygen retains the bonded electrons. So we end up with this particular intermediate. We already know this intermediate is quite unstable. So this undergoes the particular same reaction what we have seen, the tautomerization reaction. So this proton is shifted from this oxygen to this nitrogen. So we end up with the same amide. If you remember, in the acid catalyzed hydrolysis also, one of the intermediate formed is the amide. In this base catalyzed reaction also, we are getting the amide as one of the intermediate. So let us see how the amide can undergo the base catalyzed hydrolysis to produce the corresponding carboxylic acid. So in this case what happens is this oxygen is electronegative, so this pulls the electron towards itself, making this carbon little bit electron deficient, and we have a electron rich nucleophile. So this electron rich nucleophile now tries to bond with the electron deficient carbon atom. So we end up with this particular intermediate, and now during the charge reversal, this negative charge comes to the between carbon oxygen bond, and the NH2 group leaves to give the corresponding carboxylic acid, and NH2 minus ion is produced in this particular reaction. Now you may be wondering, in this particular step what happens, because between NH2 and OH, oxygen is more electronegative than nitrogen. So when the charge reversal, why not this charge reversal happens like this? The negative charge comes between carbon and oxygen bond, and this oxygen OH pulls away this electron and leaves out. So this possibility is also there, because if nitrogen is lost, we end up with a carboxylic acid. But oxygen is also equally electronegative. So why not this step happens? If this step happens, what we end up is nothing but the starting material. So this is the starting material we started off with. That intermediate, that is the amide intermediate, was present, will be regenerated in this particular step. For our product formation, the removal of NH2 is a crucial one. Unless this removal happens, we may not end up with the required carboxylic acid as our product. So next, let us look at oxidation of alkyl benzenes. So here we have a nitrotoluene which undergoes oxidation in the presence of potassium dichromate and sulfuric acid to give the corresponding carboxylic acid. And in the case of the bromo derivative, bromotoluene, potassium permanganate based oxidation in the presence of a base gives the corresponding carboxylic acids. Now, if we take this tertiary butyl benzene, this does not undergo oxidation to produce the corresponding carboxylic acid either on treatment with the KMNO4 or potassium dichromate either under acidic or basic conditions. We need to know why this oxidation does not take place. The reason is the reaction intermediate involved in the oxidation of alkyl benzene is nothing but a complicated radical mechanism. So in this particular case, the first step is the abstraction of benzylic hydrogen. So there should be one benzylic hydrogen in this particular starting material to undergo oxidation. Since this tertiary butyl benzene does not have any benzylic hydrogen, this does not undergo oxidation. So that is the reason tertiary alkyl benzenes are not at all oxidized, because we need at least one benzylic hydrogen for it to undergo oxidation. Now, in the previous reaction, we saw KMNO4 uses basic conditions. So why the slightly basic conditions are employed for the alkyl benzene oxidation for using KMNO4? Is there any reason for it? We already know even acidic condition is not favorable because the product obtained will have solubility issues, because if we are using acidic conditions and our end product is a carboxylic acid, then we have solubility issue in the reaction medium. So due to which acidic KMNO4 are not generally employed. So then what happens if we use neutral conditions? If we are using neutral conditions, that actually produces insoluble manganese dioxide as a byproduct. So this is again a big problem. We cannot isolate our carboxylic acid from the reaction medium. So that is the reason even neutral conditions are not employed. Then why we have to use a basic condition? And again, it is not a strong basic condition, it is only a mild basic condition. So in this case, the product, that is the carboxylic acid, is soluble in the organic solvent, because basic conditions carboxylic acid is present in the sodium salt or whatever may be the corresponding counterion present in the basic condition. So the carboxylic acids are soluble in the basic medium and organic solvents and water, because when we do this reaction, the solvent mixture contains water and the organic solvent to keep the alkyl benzenes in solution. So under the slightly basic conditions, the reaction medium is a clear solution because of the solubility of carboxylic acids in the reaction medium. But under acidic conditions, it will be like a suspension, due to which the reaction may not proceed to completion. So solubility is one of the reasons why the KMNO4 based oxidations of alkyl benzenes are generally carried out under slightly basic conditions. Now, the next question is, can alkenes be oxidized? Because we are talking about carboxylic acid, so let us see whether the alkenes can be oxidized. The answer is yes. But how alkenes can be oxidized? Because alkane can be oxidized, that is a combustion reaction, produces carbon dioxide and water. So in other words, if you simply oxidize an alkane, we end up with a carbon dioxide and water. But if we need to oxidize alkanes to a carboxylic acid, can we do it? Unfortunately, no. We cannot oxidize alkane to carboxylic acid directly. It is not possible, because the alkane are the most reduced form, whereas carboxylic acid is the most oxidized form. So if you look at the oxidation levels, alkane is the most reduced one compared to acid, which is the most oxidized form. So alkanes cannot be oxidized to carboxylic acid very easily. But there are conditions using very harsh conditions and high temperatures may oxidize alkanes, But generally under normal conditions, alkanes are not converted to carboxylic acid by oxidation. But we know alcohols and aldehydes can be converted to carboxylic acids. Now, we have three examples here: alkane oxidation versus arene oxidation versus alkyl benzene oxidation, because we know alkyl benzene can be oxidized to carboxylic acid, whereas alkanes like methane cannot be oxidized. The same way arenes, benzene cannot be oxidized. So why this does not happen? Because we already know alkanes cannot be oxidized to acids. Arene also cannot be oxidized, but alkyl benzenes can be oxidized, but except the tertiary alkyl arene, other alkyl benzenes can be oxidized. The reason is the CH bond dissociation energy, because in the previous slide we had seen the benzylic proton is very essential for this reaction to occur. So if we look at the CH bond, the CH bond dissociation energy is 102 kilocalories per mole for methane. It is a very high energy, so that means we have to supply a lot of energy to break this bond. So if this bond is broken, then only we can get the corresponding carboxylic acid unit is possible. So we have to break the CH bond, which is having a very high energy. So this is quite drastic conditions are required to break this particular bond. And if you look at the benzene substrates, so here again it is having 106 kilocalories per mole. This again is much higher than the CH bond breaking energy. So benzene is also not easily oxidized. But when we take about alkyl benzene, they have a bond energy which is around 77 or 78, which is much lower than the corresponding alkane or arene CH bond energies. So toluene methyl group, especially we have taken the example of toluene methyl here, group here. So this CH bond can be broken down in the initial step for the benzylic oxidation. So that is the reason alkyl benzenes can undergo oxidation under KMnO4, slightly basic KMnO4 conditions. The next one is the malonic ester synthesis. In this case we have a malonic ester. For convenience I put this particular group as E. So you can see here the E represents nothing but the ester unit, and this when treated with Rx in the presence of sodium hydroxide produces corresponding acid. Let us see how the reaction actually proceeds. So we have the starting material here. When treated with the base, this is a base, this is acidic hydrogen. Because of the two electron withdrawing groups, these protons are highly acidic in nature, so they can be easily abstracted by the base. So the base abstracts this particular proton, which produces an anion, and this anion when treatment with alkyl halide, we know this substitution reaction. So this sodium halide is removed in this reaction, so that produces the corresponding intermediate like this diesters. This on hydrolysis produces the dicarboxylic acid. So in the starting material we have both the protons. So one of the proton is removed by an alkyl group here in this particular case. So this on hydrolysis on heating produces the corresponding RCH2COOH. So this is how malonic esters can be converted to corresponding carboxylic acids. So here one of the proton is replaced by the alkyl group. So whichever the alkyl halide we are using here, that is introduced here. Then the next one is a simple and the easy hydrolysis of esters. So esters can be hydrolyzed under acidic or basic conditions to produce carboxylic acid and alcohol. So this is a very simple and straightforward method. Another important method what we will see is the ardent ester synthesis. So in this particular case, an acid chloride is treated with the diazomethane. So this reaction produces a diazoketone which is quite unstable. Generally these intermediates are not isolated when we carry out the reaction. So this diazoketone on treatment with the silver oxide followed by heating produces a ketene intermediate. This is highly unstable species. So the ketene intermediate on hydrolysis produces the carboxylic acid. So if you look at here, we have a RCOCl, we have RCH2COOH. So that means in this particular reaction, we have one carbon homologation. So that is, in this particular case also, we can increase one carbon chain length of the starting material. So we have already seen in the earlier cases, the primary alcohols when treated with alkyl halides followed by Grignard reaction, or alkyl halide and cyanide reaction produces carboxylic acids with one carbon extra, that is the homologation. So Ordine ester synthesis is also another method by which we can convert a carboxylic acid to one carbon homologation product. The next one is preparation of phenolic acids. So in this particular case, we are using carbon dioxide as a source for the carboxylic acid unit. So phenols when treated with sodium hydroxide forms the sodium phenoxides, and this on treatment with CO2 under high pressure conditions produces the corresponding sodium salt, which on acidic hydrolysis produces the corresponding hydroxybenzoic acids. So this is another method for preparing carboxylic acids. Now let us look at reactions of acids. So the acids have lots of functionalities. We have an oxygen-hydrogen bond, we have a carbon-oxygen double bond, we have a carbon-hydrogen bond. So there are various bonds are present in this functional carboxylic acid. So we can also expect various reactions based on breakage of different type of bonds. And in fact, this oxygen is more electronegative than carbon, so this is electrophilic in nature. So this also can undergo some sort of reactions. Let us see what are all the different reactions an acid can undergo. The first one is, as I shown here, we can break the oxygen-hydrogen bond. So this reaction is simply called as solvolysis or acid dissociation or neutralization reaction. Because once you remove this proton, this is the acidic proton, once you remove the acidic proton and treat with a base, we end up with the salt of this particular carboxylic acid. So that is what is the neutralization reaction. Or when this dissociates, this becomes like a H plus and the COO minus ion. So that is what is the acid dissociation reaction. So these are all two reactions which can be obtained by the breakage of OH bond. So the next one is, here oxygen is electronegative in nature. So this bond is polarized towards oxygen. So this carbon becomes electron deficient. So any nucleophile can attack this particular carbon. So that is what is a nucleophilic substitution reaction. Some of the examples include esterification, formation of amides, acid chlorides. All these reactions are nucleophilic substitution reactions of carboxylic acids. We will see them in detail in this session and in the couple of next sessions as well. So the next unit is, we have a COO. So COO is nothing but the carbon dioxide. So the carboxylic acid can also undergo decarboxylation by the loss of CO2 group. So this is also one type of reaction that is possible. And we have a alpha hydrogen, as I mentioned here, CH bond. This alpha hydrogen can be replaced. So some of the reactions that include halogenation reaction. So these are all the various reactions a carboxylic acid can undergo. We will see one by one separately. The first one we will look at is the Fischer esterification of carboxylic acids. So we have a carboxylic acid here that is treated with the acidic conditions. Here we will see the acid catalyzed reaction. So H plus is present in the medium. We already know the oxygen is electron rich, so this will try to bond with the proton, and the initial step is the protonation of the carbonyl oxygen of the carboxylic acid. So this is the initial step under acidic conditions. Once a proton adds to the oxygen, we have a oxonium ion as shown here. So the oxygen is electronegative, we already know. So in that case, what happens is this carbon oxygen bonded, double bonded electrons are pulled towards the oxygen, which makes this particular carbon electron deficient. So the lone pair of electrons on the oxygen from the alcohol is given to this particular carbon. So we end up with this kind of intermediate where the oxonium ion is present on the alcohol oxygen. So this loses a proton to produce the corresponding intermediate as shown here. So again this carbon has 1, 2, 3. 3 electronegative oxygens are present on this particular carbon. So this is quite unstable. And we have a proton in the medium, that is the solvent has H plus ions. So this oxygen which is having a lone pair forms a bond with the proton. So in this case the oxygen is having a positive charge, so this is an oxonium ion that is formed in this particular case, and we already know this oxonium ion is an unstable species, and this pulls the electron towards itself. This carbon actually now becomes electron deficient. To compensate the loss of electrons on this particular carbon, this lone pair of electrons from the oxygen is transferred. So that leads to the loss of water molecule. So here in this particular case, none of the groups can be easily lost because they are not good leaving groups. The OH is not a good leaving group, OR is also not a good leaving group, but water molecule H2O plus is a very good leaving group. So the abstraction of the proton is very crucial for the loss of water molecule in this particular step. So that leads to, since the oxygen had given out the electrons, so this oxonium ion is formed where the carbon oxygen double bond is present. Since oxygen cannot have a positive charge, so this hydrogen is lost as a proton by giving this bonded electron to oxygen, which leads to the final ester formation. So this is how the acid catalyzed esterification of acid proceeds. In the first step, a proton was included, and in the last step the proton is lost. So that means this is a catalytic reaction. In other words, this reaction is a acid catalyzed reaction. Now let us look at the acidity of acids. So the carboxylic acid, when treated with water, produces the carboxylate anion and H3O plus is formed. So what is the important parameters that affect the acidity of carboxylic acids? So the important thing is the tendency of the carboxylic acid to give up a hydrogen in the aqueous solution. That is why we call this as a acid, and there is a measurable equilibrium exists between acid and its ions. So this is what is the crucial thing for the acidity of acids. If we take alcohol can also dissociate into H plus ion and RO minus ion, but this dissociation doesn't have any measurable equilibrium. So this equilibrium does not exist. So that is the reason this carboxylic acid dissociation equilibrium only exists. So that is how we can say acids are much more acidic. And if we have to write a dissociation of carboxylic acids, we can write like this. The oxygen is electronegative. So this oxygen can pull the electron towards itself, then making this oxygen has a lone pair here. So there are, if possible, can we write a resonance structure for carboxylic acid? Let us say here there is 2 electrons. So these electrons are shifted between this carbon and oxygen because this double bonded electrons are pulled by the oxygen. So this oxygen now becomes a negative charge. Since this oxygen lost the electrons, this becomes a positive charge. So this is one type of resonance structures we can write, but can we write this resonance structure or not? We will just see now. This carboxylic acid can lose a proton to give a carboxylate ion. So in this carboxylate ion, what happens? This electron can shift towards like this, and this can be going like this. So we have this oxygen becomes O negative, and this electrons are shifted between these carbons, so this becomes a double bond. So these two structures cannot exist because these are non-equivalent structures. So due to which this does not exist, the carboxylic acid never exists in this particular fashion, whereas this is a carboxylate anion, this is a resonance stabilized, and this exists. So that is the reason this is a non-existent or non-equivalent carboxylic acid is present here, because we have a negative charge and a positive charge on the same compound. So this is quite unstable species. So this generally does not exist. Whereas the carboxylate ion has a resonance stabilized structures, so this is quite stable. So that is one of the reason the H plus ion can be easily lost to give the corresponding carboxylate anion. That is the crucial thing for the acidity of carboxylic acids. Now, how do we know the resonance structures actually exist for the carboxylate anion? So this is the biggest question we have to answer. Now if we take formic acid and the sodium formate, we have two types of compounds that is present. One is a stable carboxylic acid, another one is a carboxylate anion. So do they actually exist? And when we actually do the X-ray crystal structure studies, it has been shown that the carbon-oxygen double bond length is shown to be 1.23 angstrom, and the COH bond length is shown to be 1.36 angstrom. So in other words, we already know that double bonds are shorter than the single bonds. So this bond length is shorter compared to the longer COH bond. Whereas in the case of sodium formate, this C oxygen bond and this C oxygen bond both are having same length. In other words, this is not very short like a double bond. This is also very not long like a single bond. So this is in between 1.23 and 1.36. So the value is 1.27. So it is neither a single bond nor a double bond. So that is why we say the resonance structure exists for the carboxylate anion. So this is one of the conclusion by which we can confirm that carboxylate anions are having resonance structures. Let us look at what are the characteristics of some acid catalyzed esterification reaction. So in the esterification reaction, basically the oxygen of the alcohol is retained. In other words, if we have the RCOOH, simply the hydrogen is replaced by R dash, that is also possible, or this OH is lost and this RO is incorporated. So there are two different ways how an acid can be converted to an ester, but using labeled experiment, it is confirmed that the labeled oxygen is retained in the final product. So the labeled oxygen from the alcohol is retained in the final ester. So that clearly says that the oxygen for the ester unit comes from the corresponding alcohol. So in the esterification, every step is a reversible reaction, and any bulky groups that is present in the carboxylic acid or the alcohol carbon. So in both the cases, the functional group which is present on the carbon, if it is having very bulky groups, they do not undergo esterification very easily. In other words, the bulky group that is present on the functional group carbon, that is here either on the carboxylic acid or as shown here in the alcohol, in both the cases esterification is hindered if bulky groups are present. And in the esterification, what happens is the OH group is actually replaced by the OR group. In other words, this reaction is called a nucleophilic substitution reaction. Let us look at how acid can be converted to acid chloride. So the first one is carboxylic acid when treated with thionyl chloride produces acid chloride, sulfur dioxide and HCl. The carboxylic acid can also be treated with PCl5 to give the corresponding acid chloride, or we can also use PCl3 to produce the corresponding acid chloride. So there are three different ways by which a carboxylic acid can be converted to acid chloride. So this thionyl chloride method is the most preferred one because sulfur dioxide and HCl are gases which escape from the reaction medium, so that the reaction goes to completion very efficiently. So this is the most preferred method for the preparation of acid chlorides from acids. Then the condensation of acids with ammonia or amines. So when a carboxylic acid is treated with aqueous ammonia, we end up with an ammonium salt, and this on heating produces a primary amide. What we end up is RCONH2 because we are using ammonia as a starting material. And if we use a primary amine, that is R prime NH2 is treated with the carboxylic acid, we again get a similar ammonium salt which on heating produces a secondary amide. In this particular case, the nitrogen is having an alkyl group on this one. So this is what is called a secondary amide. And if we do with the secondary amine, we end up with a tertiary amide. So these are all the different ways by which ammonia or the amines react with carboxylic acids. Now the condensation of carboxylic acid to give anhydride. So two molecules of carboxylic acid can combine together in the presence of a dehydrating agent, especially P2O5 on heating produces anhydride. So simply what happens is one OH and one hydrogen from one of the carboxylic acid unit and the other both combine together by the loss of water molecule to produce the anhydride. If we use different carboxylic acid, then there is a possibility that we will end up with all the mixture of anhydrides. So that is the reason generally anhydride formation is not a very favorable reaction unless for a symmetric anhydride. We will also be studying about the preparation of anhydride later in this particular and the next couple of sessions. So if we take succinic acid and treat with P2O5 and heating, that produces succinic anhydride. It is a cyclic anhydride which is used in many reactions. The next one is decarboxylation of carboxylic acid. So carboxylic acid when treated with sodium hydroxide produces the sodium salt, which on heating with the calcium oxide produces alkane and carbon dioxide. So the reaction mechanism, if we look at the carboxylic acid is converted to the sodium salt. So here we have the O minus ion. So this negative charge comes between carbon and oxygen bond, and this is the carbon-carbon bond is broken. So when this happens, the CO2 moiety is separated. So this produces a RCH2 anion, and this RCH2 anion can abstract a proton from the solvent molecule to get converted to an alkane. So that is how carboxylic acid can be converted to an alkane. Then let us look at some of the reduction reactions of carboxylic acid. Carboxylic acid on treatment with the lithium aluminum hydride followed by acidic workup produces a corresponding primary alcohols. So the number of carbons from the starting carboxylic acid and the primary alcohol remains the same. We can also treat the carboxylic acid with the borane followed by acidic hydrolysis produces the carboxylic acid. So this we had seen in the preparation of primary alcohols also. The next one is homologation. So the carboxylic acid on reduction with lithium aluminum hydride followed by hydrolysis produces the corresponding primary alcohols. So this primary alcohol can be treated with the thionyl chloride to give the corresponding chloro derivative. So this chloro derivative can be treated with sodium cyanide to give the corresponding nitrile or the cyano derivative. This cyano derivative on hydrolysis produces the corresponding carboxylic acid. So by that, if we have RCOOH as the starting material, we end up with a RCH2COOH. So one carbon is added, that is the homologation of the carboxylic acid had happened through the reduction followed by other functional group transformations. The next reaction is the halogenation reaction, that is the alpha halogenation reaction. So the name reaction for this particular transformation is Hell-Volhard-Zielinski reaction. So here the alpha hydrogen from with respect to the carboxylic acid is converted to a halogen. So the carboxylic acid when treated with halogens in the presence of phosphorus gives this particular halo derivative. For this reaction to happen, the phosphorus is very important for this reaction to happen. In the absence of phosphorus, this reaction does not produce measurable yield of the corresponding halo derivative. We will now find out why phosphorus is important for this particular reaction. So in the initial step, what happens is phosphorus reacts with the halogen to produce the PX3 or PCl3 or corresponding phosphorus trihalide is formed in the first step. So this trihalide reacts with the carboxylic acid to give the acid chloride. Because this reaction we have already seen earlier, carboxylic acid can be converted to acid chloride by the treatment with PCl3. So the same reaction produces the carboxylic acid chloride. And this carboxylic acid chloride undergoes tautomerization to give this particular intermediate. And this particular intermediate can react with halogen atom. So this particular intermediate is quite unstable. So the oxygen-hydrogen bond comes between the carbon-oxygen bond, and then this double bond actually reacts with the electrophilic end of the halogen, and the chloride is lost as a Cl minus. So here we have a hydrogen plus, here we have a Cl minus. So these two combine to give HCl, that is a loss of HCl from this particular intermediate produces this halo acid chloride. So this halo acid chloride on treatment with another molecule of a carboxylic acid produces the carboxylic acid and RCH2COCl. So nothing but what happens is this hydrogen is replaced here to give this OH replaces the chloride to give the corresponding carboxylic acid, and that leads to the RCH2COOL as the acid chloride as the second unit, because whatever the chloride that is lost from this one is added here. So in other words, there is a exchange of the Cl and the OH happens. So between these two molecules, that leads to the alpha halo substituted carboxylic acid and acid chloride is produced. Since this acid chloride is the same like here, this can again undergo the reaction, tautomerization and treatment with halogen produces the corresponding acid chloride. So that way we can make this reaction complete to get all the substitution of the alpha hydrogen. The next one is the Hunts-Decker reaction. So in this particular case, the silver salt of a carboxylic acid is treated with bromine to give a alkyl halide with the loss of carbon dioxide, and silver bromide is formed as a precipitate. So here if we have n number of carbon atoms, here we will have n minus 1 number of carbon atoms. So there is one of the carbon is lost from the starting carboxylic acid. So if we look at the mechanism of this reaction, The initial step is the formation of hypobromide. So this is one of the initial step, very crucial step. This hypobromide undergoes radical cleavage because this OBr bond is facile bond which cleaves homolytically to produce a radical. So this radical loses carbon dioxide molecule to give a alkyl radical, and this alkyl radical and the bromo radical both combine together to give the RBr. So this is how the silver salt is converted to corresponding alkyl halide. The next one is Hunsticker decarboxylation reaction. In the previous one we had seen the carboxylic acid is converted to alkyl halide. Here we are actually simply going to see, instead of the halogen treatment, if we simply heat the silver salt of the carboxylic acid, this reaction we have already seen, so the initial formation is the alkyl halide. So that alkyl halide on treatment with sodium hydroxide produces the corresponding primary alcohol. So this primary alcohol can be oxidized using potassium dichromate to give the corresponding carboxylic acid. And in this particular case also, if you look at the carboxylic acid has RCH2COOH, but the final carboxylic acid what we obtained has one less carbon atom. So that is why this is a decarboxylation method. So one carbon less happens during the transformation of various reactions. Let us identify the product from the following reaction. So this isopropyl benzene on treatment with the KMnO4 in the presence of mild basic conditions and heating produces benzoic acid. And if we take this bicyclo derivative, this on oxidation produces a dicarboxylic acid. And if we take, this is a tertiary carbon, and when it undergoes oxidation only, this benzylic bond is broken, so that leads to this tertiary butyl unit remains as it is and the carboxylic acid is formed. In summary, let us recap what we have studied so far. We have studied about various preparation methods of carboxylic acids. We have studied the oxidation methods, that is how primary alcohols can be oxidized to corresponding carboxylic acid, how secondary alcohols can be oxidized to carboxylic acid under drastic conditions, how aldehydes can also be oxidized to carboxylic acid. So these are all the various methods we have studied about oxidation of alcohols. We also have studied about the Grignard reaction, how Grignard reaction can be used using carbon dioxide to create carboxylic acids. We also have studied about various hydrolysis methods, mainly ester hydrolysis, how that can be used to make carboxylic acid. And we have also studied about special methods of phenolic acid preparations. And we also have studied about reactions of acid, mainly the esterification, both acid and base catalyzed esterification reactions. We have studied about the conversion of acids to acid chlorides, amides and anhydrides. And we have studied about the various reduction methods like lithium aluminium hydride reduction and similar reductions of carboxylic acid. We have studied about alpha halogenation of carboxylic acid, Vollard-Zielinski reaction, and we also have studied about the Hunsticker reaction and Hunsticker dehomologation reaction. So with this we conclude this session. Thank you.